Happy Monday, everyone. Okay, so like Dr. Price was saying, this is not the most interesting lecture that we're going to have. We'll just be straight about that. I'll even say in last lecture, I did see quite a few students just completely conked out. And I don't blame you for this one, I'll be completely honest. Normally I'd be a little offended, but not on this one. That being said, like Dr. Price was saying, nomenclature is still important to understand. The biggest reason we want to teach you all of this is because we want to talk to you like chemists. And oftentimes it is simply so much easier if we can say like, yeah, we're talking about 2-chloro-butene-4-oic acid. And if we all know what that means, then, great, we can move on, talk about it, and learn some principles. Likewise, as Dr. Price was saying, this is, absolutely something that the MCAT, the DAT, etc. are going to just love. They're going to throw this at you. And so for those purposes as well, good to know. But that being said, probably the most important thing is to just be able to read the name of a molecule and start to build a sense of how to piece together what that molecule looks like from its name. That's sort of how I would measure, success in this topic. Piecing together a molecule from reading it. So, I will also say that anything that we learned today is internationally standardized. There's an organization that does all of this. It's called IUPAC. So IUPAC. So we're following the IUPAC standard, which means that if there's any questions, any confusions, or anything of that sort, this entire lecture is extremely Googleable. IUPAC just has a website where they list the 1,000 rules for naming molecules. And if you want to go that deep, you sure can, but that doesn't sound very fun to me. But you can do that. So that being said, imagine that you are a chemist working in a lab and you have some experiment where you need this molecule. So let's say we've got a carbon single bonded to an OH, double bonded to an oxygen, a branched carbon chain right there, we've got a bromine here. So this molecule right here, I've identified as being necessary for my experiments. So my experiment, my synthesis, whatever I'm doing as an organic chemist. The problem is I don't want to make this because this seems like kind of a pain to synthesize. It seems really convenient for using, as we'll learn in future chapters, but I don't want to make this. Luckily for me, this is one of the most sold chemicals, most distributed chemicals by chemical distribution companies, pretty cheap to obtain, which means my only issue to obtaining this is money and naming it. How do I Google this thing? And so, hopefully by the end of today/Wednesday, we will be able to piece together that the name of this molecule is 2-bromo 3-methyl butanoic acid. So 2-bromo 3-methyl butanoic acid. So again, hopefully by the end of this chapter, we will fully know where that name came from. So a chemical name, I believe that we talk about this a little bit. Is it Chem 105 or 106? Maybe both. 106. It's like we kind of talk a little bit about naming organic molecules. Here, of course, things are going to get much more complicated. We didn't see something like this in Chem 106. So when we're naming these molecules, there are three parts to the name that we need to piece together. So there is a prefix, there is a root, and there is a suffix. Now, I should have done this in last lecture. So if I'm to highlight these just for your own note-taking reasons, my prefix, so you know, is quite long. So that is all that right there. My root is this little portion right there, and my suffix is that portion there. And again, just for your own note-taking purposes, we'll talk about each of these, the prefix, the root, and the suffix. So what each of these are communicating is first our prefix is telling us what functional groups do we have. So what functional groups? By functional group, we mean like what interesting portions of this molecule are there. So you see here there's a 2-bromo-3-methyl. So there's an interesting bromo, there's an interesting methyl somewhere in my molecule. Next it tells me where. So where are my FGs? Where are my functional groups? For my root, what that's communicating to me is my main chain. So what is my main chain? Usually that means what's my longest carbon chain. More precisely, what's my longest carbon chain with a highest priority functional group? But we'll talk about that. So what is my main chain? And as for the suffix, I am communicating what is my highest priority functional group, which also kind of translates into essentially what type. I'll put that in quotations. We'll define that when we get to it. What type of molecule? So that's what these are all communicating. So the prefix telling us what functional groups do we have and where are they. My root is telling me my main chain, and my suffix is telling me what my most important functional group is, and sort of the class of molecule that I'm working with. So looking at this again, so my root, I'm working with a butane molecule. And my suffix, so this is a type of oic acid, a carboxylic acid, which also communicating that carboxylic acid is my most important functional group. So now talking about each of these individually, we're going to start with the root. So the root portion of our molecule, like I said, that's communicating information about our main chain. So let's first look at a molecule that is essentially only a main chain. So let's look at this. So this molecule here. So what I want to say in my root is primarily how many carbons are there in this molecule. So I've got in here 1, 2, 3, 4, 5, 6, 7, 8 carbons. So what I would call this then is an octane. So octane. So this molecule, it doesn't have any functional groups, there's nothing interesting to it, so it's basically just a root, so I can call it that. So octane. If I had a shorter molecule, let's look at this. So So 1, 2, 3, 4, 5. This would be a pentane. If I had, something else, there's a root for that. So we simply use our normal roots to communicate how long is our chain. Now, the prefixes that we can use in our root, so not the molecular prefix, but the root prefix, is just numerical roots. That being said, it is different for carbon chains of length 1, 2, 3, and 4. So for the first 4 kind of lengths of carbon chains, named a little different. Everything after that, we just use our normal English skills for those. So if I have a carbon chain that is only 1 carbon long, so 1 carbon is going to use the prefix meth. So an example molecule of that would be CH4 as methane. So we all know methane, I'm sure, well acquainted with it. If we have 2 carbons, that's going to use the prefix F. An example molecule of that is CH3CH3, which is ethane. Next, if I have 3 carbons, that is going to use the prefix prop. For example, if I just have a 3 carbon chain, that is propane. Once again, another molecule that we're likely well acquainted with. And then if I have 4 carbons, that is going to use the prefix bute. For example, if I have a 4 carbon chain, that is butane. Also a molecule that we're pretty well acquainted with. That's lighter fluid, if you didn't know. So butane. So methane, ethane, propane, butane. Now, like I said, after that, we'll just use our normal prefixes. So 5 carbons is just going to use the prefix pent. 6 carbons is going to use the prefix hex. 7 carbons will use the prefix hept. 8 carbons will use the prefix oct. 9 carbons uses the prefix non, and then 10 carbons uses the prefix dec. Now, if you're interested in going beyond 10, good for you, but I don't want to think about those. For some reason, that's where our English ability tends to stop for most people. So I know they exist. I've had to look them up before. I've promptly forgotten the prefixes immediately after using them. They do exist. But so that's how we name those molecules. So if we only have a root, or if we're building the root, we just need to know those prefixes and how long our carbon chain is. Now, that being said, we can start to modify our root a little bit to make these, to add a little bit of variation to further communicate information about our molecule. So let's now instead look at a variation of octane. 6, 7, 8. Let's throw on a double bond onto there. Or let's throw on a triple bond. 7. So if I have a double bond or a triple bond, that's going to modify the name of this slightly. Now, this isn't going to give us the full name of the molecule, but just to preempt this, if I have anywhere a double bond, this is going to become an octene. So my ane is going to become ene if I have a double bond anywhere in my molecule. Now, if I have a triple bond anywhere in my molecule, it is going to become oct-ine. So my ane is going to become ine. Now, this doesn't tell the full story. For example, if I have multiple double bonds, so let's say I have this molecule. That's still an octene. But now I'm starting to get confused. I need more information. Or what if I just put it in a different place? What if I just put the double bond there? It is still an octene, but where's that double bond? If I want to purchase this molecule, I care about the location of that double bond. So, but as for just the class of molecule, as for the main chain, I can say that the main chain is an octene, an octine, a pentene, a butene, a butyne, whatever. So what I can do to specify a little bit more information is I can number my carbons, and I can start by telling us the location of this double bond or this triple bond. So if I have, let's look at these two here, this octene and octine, the first ones. I want to number my carbons to give the lowest numbering to my double bond, my triple bond. So my two options, I can go from left to right. So 1, 2, 3, 4, 5, 6, 7, 8. Or I can go from right to left. 1, 2, 3, 4, 5, 6, 7, 8. So there's a clear winner here. I can either have a double bond on the carbon 7 and 8, or I can have it on that carbon 1 and 2. Yeah?
If there are any more functional groups on that or different atoms, would that change the way you number it?
Yeah, so the question is if there's other functional groups on the molecule, does that change our numbering? Absolutely, and we're going to get to that. So if I'm wanting to minimize my numbering, there's a clear winner here between the 7, 8, and 2, 1. So I'm going to choose that 2, 1 option. I'm going to say that my double bond is on carbon 1 and carbon 2. So when I'm naming this then, I will say the location right before I say ene. So this is going to become oct1 ene. Now I don't need to say oct1 2 ene because it's connecting two carbons that are next to each other. It has to be that way. So I don't need to specify the 2 anywhere, so this would just become oct1 ene. Now the same thing over here. I would number this 1, 2, 3, 4, 5, 6, 7, 8, turning this into oct1 ine. Yeah?
Is it wrong to say oct7?
If I call this oct7 ine, yeah, so if I numbered it the other way, so yeah, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so if I called that oct7 ine, does that communicate what the molecule is? Yeah, it does. But IUPAC has said that that is wrong, and so that's what we have to go with. So IUPAC says we must minimize our numbers. So we need to number our molecule that gives the lowest numbering to our interesting parts of our molecule. So again, if you're talking to me and you say, hey Nate, can you grab the bottle of oct7 ine? I would know what you're talking about. I, as a human who's allowed to reason through things, I get it. But IUPAC doesn't allow that. And if you're going to make an international standard that the whole world is going to use, it makes sense, hopefully, that we have to follow their rules. So correctly, if you're going to find this on Google, you would have to say oct1ein. Yeah?
Just a quick question for you. So I've also seen it in the book where it was just one octene. Does that also work, or does it have to be in this form?
Good question. So actually let me cross that out to say it doesn't work. So could I say, so the question is it okay to say oct1ein? Is it also okay to say, so is that the same thing as one octine? So the answer is yes, that is okay to call this one octine. However, I will caution you against that. So yeah, you can Google one octine. You can Google 4 octene, and that will get you the correct result. However, once we start seeing more interesting molecules, you will quickly regret that, like more functional groups, you will quickly regret that decision to lock yourself into that naming scheme. Again, it will work, just be careful, and we'll see why in a moment, yeah?
So there's a double bond on our 2-bromo-3-methyl-butanoic acid. Where did this, I don't see it in your
Yeah, so in here, there's a double bond here, so why is it not an alkene or an alkyne? Yep, because we're double bonded to the oxygen. So alkene, I should say here, there are general names for single, double, triple bonds. So if it's only single bonds, then the general name for that molecule is an alkane. And that's so that we can use this vocabulary term throughout the semester. So an alkane is referring to something with only single bonds. So even one double bond, the general name for this molecule is now an alkene.
So the point here is the double bond is between carbons, right?
Oh, yes, between carbons. So a carbon-carbon double bond. And then if there's even one carbon-carbon triple bond, that becomes an alkyne. So again, that's the general name for these. So alkane, alkene, alkyne, but those are only referring to, again, carbon-carbon bonds. If I'm double, triple bonded to something else, it's something different. It's a functional group now. Yeah?
So how would you name an alkane that has a double bond in the middle of the molecule? Will you just choose the lowest number carbon that the double bond is connected to?
You would. In fact, let's talk about both of these other octenes now. So this one, if my double bond is somewhere else, so once again, let's just do what I said to do. We'll number our carbons to give us the lowest possible numbering scheme. So I've got two options. I've got 1, 2, 3, 4, 5, 6, 7, 8. And I've got 1, 2, 3, 4, 5, 6, 7, 8. So here my options are 3, 4, and 5, 6. There's a clear winner there. So the one that gives us the lowest numbers is going to be the one in red. So I would name this molecule oct, and then once again I'll use the lower of the two numbers for the alkene. So oct3. And that now tells me exactly what I'm looking for. And if you choose to, you can pull out your phone, Google oct3ene, and you will see this molecule. Now, what if I have multiple of something? Oh, yeah?
So you're never going to see like the max carbon, like 8 for octene?
Yeah, will you see like the max number in an octene, octine? No. For other functional groups, maybe. When we get to that. But yeah, not for octene, octine. So now if we have multiple, we have a way to communicate that as well. So if I number these, So 1, 2, 3, 4, 5, 6, 7, 8. So this molecule, I will just say it's symmetrical. We can number it the other way too, but you get the same numbering. 1, 2, 3, 4, 5, 6, 7, 8. We would see we have a double bond on 1 to 2, 3 to 4, 5 to 6, 7 to 8. Just like in the other numbering, 1 to 2, 3 to 4, 5 to 6, 7 to 8. So if I want to name this molecule, I will simply say the location of all of the double bonds. So I can say that this is an oct, and then I have a double bond on carbon 1, comma 3, comma 5, comma 7, and then I would use now an extra little prefix to say how many of these I have, even though it's redundant, but I don't make the rules. Tetraene. Tetraene, tetrene.
You know, there's probably a rule for that. Like somebody asked me last hour about the oct, right? Is it octa 1357 tetraene, or is it just oct 1357 tetraene? There's probably a rule for that, and we do not care.
Yeah. Yep. So oct oct or octa, who knows? Oct 1357 tetraene or tetrene. Yeah?
Is there any reason there's dashes around the 7?
There are special pretentious IUPAC reasons for that. I think the official reason is that dashes communicate every new functional group or something like that.
The question was why you got a dash before the 7.
Oh,
You said comma, but
did
you
I
put
do
a dash.
that? My bad. Okay.
I was like, oh no.
Okay, yes, I see what you're saying. That should be a comma. Yeah?
So for example, if it was like 3 double bonds, would it be just propene?
So if it was 3 double bonds, it would be triene.
Oh.
Yeah, so IUPAC's awesome, isn't it? So for functional groups, we'll just use, di, tri. So yeah, it could be diene, triene, and so on. Awesome that they're not even consistent with themselves. It's probably historical, the reason they're doing that. It is what it is. We have to play by their rules. Yeah?
So if there's one double bond, it's not methane, it's just
Yep. Yeah. Yep. So you won't use a prefix for 1.
So yeah, that's an important point that some of you may be also wondering about. You know how to count carbons in a chain with meth for 1, F for 2, prop for 3, and bute for 4. That's the only time we use those. For anything else that we have more than one of, it's di, tri, tetra. And if there's just one, there's no reason to say mono. You just leave off that, and that communicates that you just have one. So nobody says octamonoene. We just say octene. There's one double bond.
Yeah.
So if you had a combination of bonds, for example, if between 3 and 4 was a triple bond and the rest are doubles, how do you indicate where the position is of each of those?
You're gonna love this.
So if we had this molecule, what would we do? Is that the question? Okay. So if we have a molecule like this, so is this an alkene or is it an alkyne? It's both. Yep. So now this is where I really want to emphasize that what we're learning is not principle based. In fact, it's not fair to say, is this an alkene or is it an alkyne? I could maybe say, well, right here is an alkene, but then right here is an alkyne. So what is the molecule? I don't know. It's a hard carbon chain. So let's do what we did before. Let's number our carbons. And just for speed, I don't think I need to number it both ways. I have an alkyne on carbon 1, so that'll give me my minimum numbering. So 1, 2, 3, 4, 5, 6, 7, 8. So the way that I will number this, by the way, just to mention, I want to give the minimum numbering to the first thing to show up. So minimum, or minimize number to first functional group. The first whatever shows up. So now, naming this molecule, I'm going to do something similar to what I did before. I just need to communicate that both of these molecules are here. So if I have multiple competing functional groups or multiple competing objects on my molecule, I will simply organize them alphabetically. So this would become oct dash, and then alphabetically I have an ene and I have an ine. So ene comes first in the alphabet. So oct 5 ene 1 ine. So oct 5 ene 1 ine. Yes, in the back?
The way this is, coming up as docs, the way to separate the numbers between commas, there's no way to separate the numbers from the dashes.
Yeah. So the question was, essentially when to use dashes and when to use commas. So you'll use commas to separate numbers. So if it's like a diene, a triene, a tetraene, whatever. And you'll use dashes to separate, letters from numbers, essentially. That's a good way to put it. So here, yeah, so every time I'm switching from letters to numbers, I'll use a dash. Or when I see functional groups. And then anytime that I'm listing numbers, I'll use commas, like what we saw above in the oct 1357 tetraene. So, yeah, so that's how we name that, oct 5 ene 1 ine. Okay. So that's pretty much what there is to know about the root. Yeah?
Minimize number of first functional groups. When you wrote that, did you mean minimize it to the first double or triple bond, or have we not talked about minimize number of the first functional group?
So by functional group, I guess now is a good time to maybe define that formally. Formally in my most informal way. A functional group is anything interesting on my molecule. So just anything that's not an alkane. So carbon-carbon single bonds are really boring in organic chemistry. So anytime I see something different from a carbon-carbon single bond, I'm going to call that a functional group. Now, functional groups sort of define the chemistry of my molecule. So if my molecule has, right here, if my molecule has an alkene, it's going to behave relatively similar to all other alkenes out there. If I have a carboxylic acid, my carboxylic acid is going to behave similar to all other all other carboxylic acids that I can also find out in the wild. Now, of course, there's some variation, but there's a lot of general patterns we'll see. So just for here, if I call my alkene a functional group, I call my alkyne a functional group, I just want to say whichever one shows up first, that's the one that's going to get the lowest number on it.
And you guys have already sort of thought about functional groups, so you didn't know it. A lot of this business about HOMO and LUMO gets your attention focused on the part of the molecule that's most interesting. And you will see that functional groups have characteristic HOMOs and LUMOs. Alkenes, for example, the HOMO is the pi bond. You're worried about the pi bond reacting. Similar things with a lot of these that we talked about.
Yep. Okay. So now that talk about functional groups, that brings us to our suffix. So the next part of our molecule is going to be our suffix. What's our most important functional group? Or what's our highest priority functional group? So what I'm going to list for you here is essentially I have 11 different functional groups that we'll want you to know. There's a couple others on the study guide, and it talks about how to name those as well, but these are very common ones we see out in the wild as organic chemists. And yeah, so all of these will have special names for them. And as we're naming these, note that the way that we name these is our ane. So, hexane, septane, octane, whatever, is going to become, so an, and then our suffix. So for example, let's look at our first functional group, our highest priority functional group, and these are listed in order. That'll mean more once we talk about the prefix. But our highest priority functional group, I'll zoom in for you guys, is this, a carboxylic acid. And the suffix that this gets is oic acid. Now, as I'm listing these, this is one place where I would recommend get some flashcards. We really try to minimize the amount of flashcards that you need for organic chemistry. But for these functional groups and their suffixes, there's not really a great way around it. So I would recommend that. So if I were naming a molecule with a carboxylic acid, let's say that I had this. So 1, 2, 3, 4. So I've got 4 carbons with a carboxylic acid on this. My butane would become butanoic acid. So just that E will change, yeah?
In this case, we don't really care what carbon the oxygen hydroxyl group are on.
So normally we will. A carboxylic acid. So the question was like, do we care about the number of our highest priority functional group? The answer is yes, we do. But for a molecule like this where, first of all, we're just learning about the suffixes right now. And a carboxylic acid must be terminal. That means it has to be on an edge carbon. Because it has an OH on one half of it. If there were another carbon chain, then sure, we can get a little more complicated, which we will very quickly with example 2. So if we have complicated numbering, then yeah, we'll write something, but it kind of depends on our molecule.
I can't resist. Nate, can you draw ethanoic acid?
I can
Just
draw.
right below butanoic acid.
Yep.
So the molecule Nate is drawing is called ethanoic acid. It's commonly called acetic acid, and you know it as vinegar. And it's like a lot of acids, it tastes sour or tart, right? The acid above, butanoic acid, carboxylic acids in general taste tart and sour. As they get longer carbon chains, they start to smell bad. So vomit, smelly feet, and stinky cheese is often longer chain carboxylic acids, butanoic acid in particular. The smell of vomit, fantastic.
Yep. And Hershey's chocolate, apparently. Yep. Okay. Yeah. So that's our highest priority functional group. So next, we've got a fun-looking priority group. This is where we have an R group. By the way, as I'm writing this, do we know what an R group is? Are we comfortable with that? Okay, yeah, so R just stands for anything. Can be a hydrogen, it can be a carbon chain, just something boring. Usually we'll say something that's not going to modify the molecule into something cooler. That's how we normally define that. So usually a carbon chain, sometimes a hydrogen if it doesn't make it interesting. So this functional group is called an acid anhydride. And the suffix that this will get is oic, anhydride. Now, yes, there are 2 R groups on here, and you would need to name and specify those, but we're not going to worry about that right now, if that's okay.
Fortunately, they're almost always the same, and I don't actually care about naming anhydrides anymore. Just 'cause I
Yeah.
don't do that.
Yeah, they do tend to be symmetrical. You'll look at a couple anhydrides, I think in OChem 2. But yeah, if your anhydrides aren't symmetrical, they're the worst to work with, so we don't like to use them. So we'd often just say butanoic anhydride, and that would say it's a butane group on both sides. Okay, next, in order of priority, we have an R group, then double bond to an oxygen, single bonded to an OR. So now there's just an oxygen separating you from further details. This is called an ester, and the suffix that this gets is O8. Now this as well, I recognize there's 2 R groups. Don't worry about it right now. I believe the study guide talks about it, or maybe it
So
doesn't.
usually the R group on the left that's attached to the carbon that's doubly bonded to oxygen, I call that a carbonyl group. The R that's bonded to the carbonyl group is often the larger thing. The R that's bonded to the oxygen of the ester is often short and simple. So you'll name that short and simple part, say a methyl group at the beginning of the name. Then you'll name the R group and you'll end the name with O8. There's maybe a couple examples. Your mind will want to tell you, you'll want to play the what if game. Well, what if the R group attached to the oxygen were huge and crazy? And the answer is we would not bother to name that molecule. We would call it Joe or something.
Yeah. Yeah, usually in papers we'll just number them or letter them, like molecule A, molecule 1. So, yep. Okay, so next, our 4th functional group is an R group. So very similar, double bond to an oxygen, and then a single bond to an X. So X referring to a halide. So that's a fluorine, chlorine, bromine, iodine, maybe an acetine. I've never seen that, but probably would work. And this is called an acid halide. I'm going to write halide in red. Now, this will change depending on the identity of X. So it could be chloride, bromide, etc. And the suffix that this will get is oil halide. So once again, this could be oil chloride, oil bromide, oil fluoride, oil iodide, and so on. Just depending on the identity of X, yeah?
The study guide names it an acyl halide.
That's fine too.
Yep, yeah, you'll see acyl. I think oil is technically what IUPAC wants, and acyl is historical, but it's semantics. But yeah, so they both work. Next, we have an R group. Double bond to an oxygen, and then we are now bonded to a nitrogen. This is called an amide or an amide, depending on how you want to say it. I've heard it both ways. I've heard professors here pronounce it both ways. Depends on, I guess, how you're feeling on either day. It's kind of like ligand and ligand. I don't know what the right way is, but they both work. So amide, amide, those are both common ways to say this. And the suffix that this gets is amide or amide. And then our next functional group is going to be this one, finally something that looks a little different. An R group bonded to a carbon that is triple bonded to a nitrogen. And this is called a nitrile. And its suffix that it brings is nitrile. So just like with the amide. Now notice here that these first 6 are very similar in that you have a carbon that is bonded 3 times to an interesting atom. So here we have 2 bonds to an oxygen plus another bond to an oxygen. Here we have 2 bonds to an oxygen plus another to an oxygen. Down here we have, a triple bond to a nitrogen. So all of these have similar priority, and we're not really going to ask you to rank these in priority amongst each other, but we do want you to know that these 6 are going to sort of trump over the other functional groups that we're going to talk about on Wednesday. So as you're studying this, look at the study guide, by the way. This goes into all of this in great detail. We'll continue to cover it on Wednesday, but that will be a massive help to your studying, looking at the study guide here. So, good luck with your studying.